Welcome to the topic of VTK, the Visualization Toolkit. Today I'm going to cover the part 2 of our two-part series. I'm going to focus on the visualization model. Remember last time we were discussing that VTK has two object models. One is graphics model and the other is visualization model. Graphics model is perform rendering, taking the output of visualization model and generate an image. Visualization model, on the other hand, is to transform and represent the data. In terms of pipeline, visualization model follows immediately after the data source and produce output to the graphics model. And again, if you remember, there is one object called mapper sits in the middle of visualization model and the graphics model. Basically, a mapper is to convert geometry into a format that can be rendered. So now let's look at the role of visualization model in detail. Basically, visualization model is to convert data from its original form into graphical form. It mainly deals with two issues: transformation and representation. Representation is concerned with the internal data structures. How are you going to represent the data internally? And transformation is concerned with converting data to graphics. Now let's look at the example using stock price. So the image on the left is a Dow Jones Industrial Average value in a particular day. Clearly, for the Dow Jones Industrial Average, there are a sequence of numbers. Now you want to display the numbers into a plot because that's the easiest way for people to understand the up and downs of the Dow Jones stocks. So what does the visualization model do for us? First of all, representation. For stock prices, basically we need to record the prices and also the time, right? Because if you look at the plot on the left-hand side, it has values of the index from early in the morning all the way till in the afternoon when the market closes. So we are going to have two arrays. One array is to record the prices, and the other array is to record the time when those prices were recorded. Now, what is the graphical representation? Here we decide to use XY plot. The x-axis represents the time, and the y-axis represents the index values. So as you can see, the role of the visualization model is to take the raw data and store that internally as two arrays, and then display the two arrays using a graphics library to produce the XY plot. Now let's look at another example. Say you have a quadratic function defined in three-dimensional space. That is a function that you can evaluate the value at every XYZ 3D points. How are you going to visualize this function so that you can understand the behavior? So what we can do is you can, first of all, predefine a set of points that you want to sample the function. Say we can use a three-dimensional regular grid. And then you input the XYZ position at every grid point to this function and evaluate the function values, f of XYZ. You have a 3D array. Each array element represents a particular grid position, and then you evaluate and store the function value. So now you get this 3D array, so you can say that's your raw data. Or you can say this is the derived data from your original quadratic function, which is continuous in space. You want to visualize this function, so you have to determine the representation. There are many ways you can use to look at this 3D array. One method that you might use is to say, give me all the points that have a particular constant value in the function. And this is sometimes called isosurface. We are going to talk about that later in this course. Basically, the problem statement is, given a 3D array, every point has a function value. You want to find all the XYZ points that has a constant value. Now, you can visualize multiple set of points with different values. To achieve that, you can run through a transformation process to extract the points that have the set of value that you want to visualize. This is the transformation that you're going to use to convert from the raw data to geometry, which is a surface here. The surface can be represented as a bunch of triangles, and then you can use a graphics library such as OpenGL to display that on the screen. So in this example, we show that you can use visualization to convert an analytical function to a bunch of values defined in a discrete 3D array. And then you can extract all the points that have a constant value and represent those points using geometry, that is, triangular surface in our example. When you produce the geometry, you can say that's the end of visualization model using Vtk's term. And you give the geometry to the graphics model, which will display the surface on the screen. So how is the visualization process described in Vtk? Vtk has this concept of visualization pipeline. The pipeline describes the flow of data from its original form to the final image output. The visualization pipeline can be divided into function model and object model. The function model is focused on describing the transformations, that is, the steps that are used in the pipeline to create the final visualization. In other words, how the data are flowing through the process and how are they transformed. The object model describes the objects that participate in the function model. This includes the processes and the internal data structures. Now let's look at an example of Vtk function model. The function model, remember, is to illustrate the steps that are involved to create the visualization. Now, some notations in the example here. I use rectangles to represent the processes. I use 2 bars to represent the data. And I use arrows to represent the data flow direction. Let's use the quadric function example. So we have a function f. Now I want to visualize the function. So first of all, I will sample the function. Then I will produce the point array. Notice here I use a rectangle to represent the process of sampling or evaluating the function. The result of function evaluation creates a data array, here represented as double bar. Because I want to visualize all the points that have a constant value, so I'm going to have another process that is responsible for extract all the points in the form of a surface. So the output of this process is geometry, that is a collection of triangles, for example, or polygons. And those polygons are used in a graphics library to produce the final display. So that if we only focus on the functions, that basically we are going to go through sampling, we're going to extract surfaces, and finally we need to render the geometry output. Now let's look at Vtk object model. Like I said before, the object model is used to describe the objects that participate in the function model or visualization pipeline. It contains process object. A process object operates on the data objects, or you can say transform the data objects. One example is we have a surface extraction process that convert the pre-computed function value xyz in a regular grid to a collection of triangles that have constant values. The object model also has data objects. A data object represents information and methods to create, access, and delete information. An example of the data objects is the 3D array that we use to store the function evaluations. Now let's look at some specific Vtk objects. First of all, let's look at process objects. So the figure below is the same visualization pipeline we used earlier. In the beginning of pipeline, we have a source object. The source object is to interface with external data sources, such as files. The output from the data source is going to be input to filters. Vtk has a large number of filters. You can imagine those filters are performing different kind of data transformation, and the output of filters is going to be sent to mappers. The Vtk output filters will produce visualization objects or geometry, that is, something can be visualized. But they are not quite graphics object yet, meaning they may not be in a format that can be taken by graphics rendering libraries such as OpenGL. So we need a mapper object, which is a process that is a sync of the functional model and interface with the graphics model, which may need to convert the output from the filters to something that can be displayed. So now let's back to this quadric function example. Given the visualization pipeline, the sampling of the function can be considered as a source object. The surface extraction process is a filter object. And we need a mapper to convert the output of filter to graphics model object in the form of polygons, for example. And then finally, the polygons are rendered to the screen. Now let's look at Vtk data objects. The Vtk data objects are actually the data set. Previously, we have talked about Vtk file format, that is how Vtk describes scientific data set. So here, mainly I just give you a refresher. Data objects of Vtk can be divided into structures and attributes. The structures are mainly about how the information is organized. For example, the mesh, the cells, the vertices, etc. The attributes of the Vtk data objects are the information produced by the simulation. Oftentimes, they are the information that we want to visualize. For example, pressure, temperature in a numerical simulation. About the structures of the object or dataset, we can divide the information into topology and geometry. Topology information is invariant under geometric transformation, for example, rotation, translation, and scaling. Remember, we talked about Vtk supports different cell types: point, lines, triangles, tetrahedron. Those are the topology, because even if you transform a triangle, they are still triangle. So the topology remains unchanged. The geometry is the instantiation of the topology. It deals with the size of the cell, the position of the cell, the orientation of the cells, etc. These are the different topology for the Vtk cells, or you can call that Vtk cell types. About the attributes, they are the information stored at each vertex point, or you can say at the corners of the cells. The attributes can be scalars, which is a single value, used to represent, for example, temperature, pressure, etc. The attributes can be velocity, which is vector. They can be surface orientation, called normal, which is also a vector. They can be tensors, which is matrices. A Vtk dataset is a collection of structures and attributes. They can have different type of mesh, for example, structured grid, rectilinear grid, and so on. Okay, this is the end of my Vtk overview. We just covered Vtk visualization model. The model includes the function model and the object model. So I'm hoping that now you have a basic understanding of Vtk structures. So the next step is for you to write some Vtk programs.